Swayam Prabha. Digital India. Educated India.
This Maritime Engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar Lecture Theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar.
So for design of reinforced concrete structures under fire, we have seen the material properties of concrete as well as reinforcing steel, and we have also seen assumptions behind thermal analysis. Okay. In thermal analysis, we assume that rebar is not to be modeled separately and that rebar temperature is the same as the nearby or surrounding concrete temperature. And this originates from the fact that steel is a very good conductor of heat. Okay, so whatever is the surrounding temperature, the rebar will be at the same temperature. Then we saw the 500 degree isotherm idealization, okay, which states that any concrete, first we do thermal analysis. From thermal analysis, we get contours. Okay, then we pick the 500 degree isotherm, which is the contour where temperature is 500 degrees Celsius. So the assumption of 500 degree isotherm method is that any concrete which is inside the 500 degree isotherm, that has full strength or no degradation of strength, whereas any concrete which is outside, that has zero strength, okay, or it is completely degraded. So that helps us in calculations. Then the rebars, which are either in tension side or in compression side, we consider the actual temperature which is coming from the concrete thermal analysis. For each rebar, we find out the strength reduction factor, and based on that we calculate the overall average strength carrying capacity or load carrying capacity in tension or in compression, which we had been calling FSD or FSCD in terms of tension or compression steel. Okay, and then we take those into account for moment calculations, and we saw that how moment can be, generally it has two components, mu1 and mu2. mu1 being the balanced moment or balanced section moment, and mu2 leading to the compression steel plus additional tension steel. Then we saw how A can be calculated. A was the distance of the tension side reinforcement centroid from the bottom fiber or the tension fiber. Okay. And we saw how when the reinforcement is provided in multiple layers, in that case this A can change depending on the strength at each layer. Okay. So we saw that calculation, and finally we also saw how the small d, which is the effective depth of a concrete section, beam section, how effective depth will change or can change when the temperature increases, because this d phi we are defining as capital D, which is the total section depth, minus A and A phi, right. A is the distance of the centroid of the tension side reinforcement from the tension bars. Now let us look at an example to understand how this method works. We will go step by step. So we will first do an example with actual calculations here, and then we will go back to using a computer code, because when the section sizes become reasonable or more realistic, in that case the calculations by hand becomes lengthy, and that is where we have computers for. Okay, that is what we have computers for. So in this example we have a beam which is given here. The width of the beam B is 200 millimeters. Okay, the overall depth of the beam capital D is 400 millimeters. It has been provided with two bars of 20 mm diameter. Okay, and the clear cover is 20 mm. Now if the clear cover is 20 mm and the bar diameter is 20, okay, this distance, which is what we call small a, okay, this will be 30 mm, and this is the location of the centroid of the tension side reinforcement. This is where the tensile force T will act. Okay. Then for the concrete side, this is eta FCK, and this particular thing, distance, is lambda times x, where x is nothing but depth of the neutral axis. Now if we are using FCK is equal to 50 MPa, we see that this FCK is less than 50 MPa. Okay. So for this condition, lambda will be equal to 0.8 and eta will be equal to 1. So we first we try to find out the depth of the neutral axis. For that we can simply write T equal to C, where C is the compression side force of concrete. Okay. The compression force of concrete will be the area of this stress block, which is lambda times x multiplied by eta times FCK multiplied by B. So this calculation we are doing at T equal to 0, okay, which means the fire exposure is yet to start, okay, and we will be say considering a standard time temperature curve, okay. So at this point in time there is no reduction in B, okay. So there is practically no B fire, it is equal to B. So this is the compression side force of concrete. This we will equate to T, which is 0.87 times FST times AST, okay. FST we have taken as Fy of this 415 steel, okay, and AST for 2 bars of 20 mm, each one will be 314 millimeter square. So AST is 628 millimeter square. So when we do this, we find out the location of the neutral axis X, okay. So that comes out to 70.85 millimeters. Now once we have calculated X, okay, then we can calculate the lever arm. We saw that lever arm will be small d minus 1 by 2 of lambda x, okay. Now what will be small d? Small d effective depth will be capital D minus A, okay. In this case capital D is 400, A is 30, so small d is 370 millimeters, okay. So we have 370 millimeters here and 0.5 lambda x, okay. So that gives us Z, which is 341.6 millimeters. Okay. The value of x we have calculated and put from there. This is the value of x. So now that we know the value of Z, okay, we can calculate the design moment capacity. In this case, since it is a singly reinforced section, there is no compression steel, and we are doing this only for the sake of understanding of the 500 isotherm, okay. So mu, which is the design moment capacity for this singly reinforced beam, will be either this tension force times Z or the compression force times Z. So we can take the tension force times Z, okay, that gives us the moment, and the moment capacity of this comes out to 77 kilonewton meter. So for FST we have put 415, okay, for AST we have put 628, and for Z we have put 341.6, okay. So which means initially, so this is the cold capacity, okay. So this is the cold capacity, okay. So cold capacity of the beam. Now let us go to T equal to 15 minutes, okay, which means on the fire curve, standard fire curve, we take 15-minute and read out the fire temperature, okay. Now using that fire temperature, we do a thermal analysis. From the thermal analysis, we plot these contours, okay. From the contours we find out which one is the 500 degrees Celsius isotherm, and from this isotherm we get the X500, okay. So X500 has been calculated to be 5 millimeters, which means this B, which was 200 earlier, okay, we have X500 gone from the left side, and we have X500 gone from the right hand side, okay. So from here B fire, which is B minus 2 times X500, that will be 200 minus 2 into 5, so that will come out to 190 millimeters, okay. So this is B fire 190 millimeters. Now obviously these rebars happen to be inside the 500 degree isotherm method, so the temperature of the rebar will be lesser than that, okay. So we again go back to the contours, okay. and we pick out the coordinates of the centroid of these two reinforcements. Since these two rebars are symmetrically located, temperature of both the rebars will be the same. Okay. So, this T rebar happens to be 383 degrees Celsius. From the temperature of the rebar, we will find out the strength reduction factor. Okay. So, we have this graph of KYT versus T for rebars. Okay. And we saw that the strength began to reduce for rebars at a temperature less than 400 degrees Celsius, which is unlike the structural steel where up to 400 degrees Celsius there is no strength loss. So, K rebar comes out to 0.9. Okay. Now again we go with the same calculation method. Okay. And we said that since this is a single layer, A and A fire will be the same. So, A will not change. Okay. So, if A does not change, a small d also does not change, remains the same as earlier. So, we have the compression side force here. Okay. So, lambda times x, lambda is 0.8, remember, eta times FCK, where eta is 1, and now instead of B, which we were using in the previous case, which was t equal to 0 case, we are using B fire, where B fire has been calculated to be 190. Okay. On the right hand side, again we have made an adjustment for the strength of the rebar. Okay. So, in the previous slide, we had only FST because temperature was room temperature. Now we have a strength reduction happening. So, now it is K times FST, where K is 0.9. Okay. So, we put in all the numbers. So, lambda is 0.8, so 0.8x multiplied with eta is 1, so FCK 20, and then B fire, which is 190. Okay. This is the compression side. Similarly, here we have the tension side. So, what we have on the tension side is 0.87 remains, and this K is a 0.9 factor which is coming. Okay. Then 415 is FCK and 628 is AST. So, when we put all of that, X comes out to be 70.85, which is a very little bit of increase, but practically the same. Okay. So, we put this X back and find out Z. Okay. Z has increased a little. Okay. Previous case, it was well, there is no change actually. Okay. So, it was 341.66 earlier also, and 341.66 now also, and practically there is no change because there is very small change in small reduction in K, and but there is a small reduction in B fire also. So, in a way, in terms of ratios, I think they compensate for each other. So, not much change, no change in X and no change in Z, only that in MU calculation we will have this factor K, which is 0.9. Okay. So, at t equal to 15 minute, the capacity comes out to be 69.47. Okay. So, if we write T versus MU, okay, at 0, t equal to 0 minute, capacity was 77.21. Okay, this is in kilonewton meter, and then at 15 minutes, the capacity is 69.47. Okay. Similarly, we can do say one more time step. We go to 60 minutes. Okay. So, from a thermal point of view, we are again doing thermal analysis. We have already done thermal analysis once, it does not have to be done repeatedly. So, we have done thermal analysis, we find out the contours, then X500. Okay. So, X500 in this case comes out to be 23 mm. So, this B fire will be 200 minus 2 into 23. Okay. So, this comes out to 154 mm. That is B fire. Now temperature of the rebar has increased. Okay, in this now the temperature is 444. So the strength reduction factor has also reduced. So instead of 0.9, now we have 0.8. Okay, the other calculation process remains exactly the same. There is no change. So we have lambda is 0.8. So 0.8 times x multiplied by 1 times 20 times b fire. Okay, now this is equal to, the only change here is k, which is 0.8. Okay, so now x increases a little bit. Okay, so the previous case x was 70, now it has 73, which means that neutral axis has shifted downwards. Okay, so neutral axis has shifted downwards, and taking the same nature of calculations further, we can calculate mu. So now at 60 minutes, the capacity is 61 megapascal, kilonewton meter. Okay, so we can continue the table here. For 60 minutes, it is 61. Okay, so we can notice the decline in the moment capacity, and this is how these calculations can be performed. Now let us look at a more elaborate example where we will begin to rely on the computer code, okay, that we have been discussing at various points in time of this lecture and previous lectures. So a reinforced concrete beam has a design moment of 120 kilonewton meter, which means this is the demand. Okay, so that is shown below, which means here. So B is 230 millimeters, capital D is 400 millimeters. Okay, the centroid distance of layer 1 and layer 2 are given as 40 mm, 40 mm, and 40 mm on all sides. Okay, distance between two successive layers is also given. Okay, on top it is 50 and 40. So this distance also can be calculated. So all of the geometrical parameters are available. Grade of concrete is M40. Diameter of tension reinforcement is 16 mm. So these reinforcements are 16 mm diameter, and compression reinforcement is 12 mm. So these reinforcements are 12 mm in diameter. Okay, so now let us see how we proceed with the analysis. So first, in the computer code, we start with the given data, right? And we are using SI units for everything, just to make sure that our units remain consistent. So in given data, we have B and D. Okay, so B and D is 230 and 400 millimeters. That is there. The characteristic strength FCK is 40. Okay, and here we are writing this FCD. FCD is nothing but eta times FCK. Right. So this is 1 minus FCK minus 50 divided by 200. Either this or 1, whichever is lower, okay, that will be taken. So here, since FCK is less than 50, the value of FCD will be same as that of FCK, because eta will be equal to 1. That compression and tension rebars both have the same strength, which is 415 megapascals. Okay, so Fe 415 being used, and we have also mentioned the demand moment. Before we go on to temperature calculations, one more thing I can point out is that because this FCK is less than 50, eta we said is 1 and lambda will be how much? 0.8. Okay. So with this we can use the methods here. We will notice that wherever this neutral axis lies, okay, the concrete which is effective is only above it, that is the concrete in compression, and that too within the 500 isotherm once we begin the high temperature analysis. Okay. Below only the rebar will be effective. Okay. So since in the thermal analysis we have said that only the rebar temperature need not be calculated separately, we do the concrete analysis thermal and we calculate the temperature at centroid locations of the rebars. Okay, so that is what we try to do here. So we've defined a data structure like this, okay, where this first column and second column, okay, these are the XY coordinate of the rebar, assuming that the origin is at the left bottom corner. Okay, so if this is 0, 0, okay, that is there, and the third column is the diameter of the rebar. Okay. So if you go to rebar number 1, that is the first row. So this is rebar 1. Okay, and we have labeled here them in a way that you will see that this is also labeled 1, this is also labeled 1. Okay, although in this they will appear differently. The reason we have labeled them like this is that this and this, because it's a 3-side exposure, they will have the same temperature. Okay, so they behave in a similar way. Similarly, 3 and 3 have been labeled because these two will have the same temperature. Okay, because eventually they lie on these kind of contours. Okay, 2 and 4 will have different temperatures and hence labeled differently. Now 5 and 5 also, because they are symmetrically located, they will have the same temperature and hence labeled in this way. So for rebar 1, first row, okay, x coordinate is 40, y coordinate is 40. So we have 40, 40 and 16. 16 is the bar diameter. Then we go to 40 plus 85, which is 125. So then we are talking about this row. Okay. So x coordinate is 125, y coordinate is 40 again. So this is rebar 2. Okay. Then although here we have said number 1, but this is the third row here. So this is this third row. This is 1. Okay, like this matrix is related to the rebars which are physically shown. So for this, what will be the x coordinate? 210. We add another 85. So 210 is x coordinate, 40 is the y coordinate. Bar diameter is the same, 16. So all tension bars are of 16 mm size. Then we go to the next layer and again we go from left to right. So this is, so 40 is the x coordinate and y coordinate becomes 80, which is 40 plus 40. Okay, so 40, 40 and 16, this is this particular rebar. Then we go 125, 80, 16, which is this, okay, and like that. So this particular data structure is having information of tension rebars. In a similar way, we have defined compression rebars data structure. Notice that the origin still remains at the lower bottom corner. Okay, so for this particular bar, which comes in row 1, we have x coordinate as 40 and y coordinate as 350. So this particular is coming here. And finally, for this last one, we have x coordinate as 210, that is 210, and then y coordinate same as the other one, which is 350. Okay, and for both the compression bars, the diameter is in millimeters. Okay, now since we have these internal numbers, all of them in millimeters, we have multiplied by 10 to the power of minus 3 from the outside to make sure that these coordinates as well as the diameters are in meters, because we are trying to use SI units. Then we proceed with the thermal analysis. Okay, so here we will do 2D thermal analysis, and you would recall that for Wick storm, okay, this Txy, it depends on Nx, Ny and Ns, right. So this is the temperature loop which calculates temperature at different points in time. Okay, so Nx is defined like this, Ny is defined like this, and we calculate Txy. Okay, Txy here is a three-dimensional data structure where it's a matrix stored, one matrix stored for each time step. Okay, and each matrix has xy temperature. Okay. So to see how it works, we go back a little bit. So this Ts is the time. Okay, so we are modeling up to 4 hours the thermal exposure. Then x, s and y, s. So x, we are only modeling half of it because of symmetry. Okay, that is where it goes from this to b by 2. Okay, so only say left half is being modeled. Y's go from all the way from bottom to all the way to the top. Okay, now this creates a grid. So we have this xy grid which is created using this command. Okay, it will have a matrix. So x and y will be matrices of all the x coordinates and y coordinates, and we are writing this in MATLAB. You can also use Octave, say. So it uses these special data structures, and once we calculate a function value at this, in this kind of a grid, okay, using this ND grid function, it is straightforward to draw and calculate the contours. Okay, now Tf is the fire temperature. Okay, this is the ISO 834 temperature curve. So Ns is dependent only on time, so it is calculated outside. Then Nx and Ny are calculated, and then this Txy. So this Txy, so one is for the first time step, for the second time step, and like this. Okay, so which means each element of this matrix stores temperature of each xy coordinate within this section. Okay, that is how this data structure is given. Now that we have the contours, we need to find the 500 isotherm. Okay, we will have a little bit of discussion on how to find this also at the at a later stage of this this lecture. But for now, let us say we have found this 500 isotherm. Okay, so as we saw in the hand calculations, this B fire will be B minus 2 times x500. Okay. This capital D fire also can be defined, although it is not required for calculations. Okay, that is capital D minus y500. Okay. Once we have found the reduced cross-section values and the isotherm method, isotherms, 500 isotherm, we need to calculate the strength reduction factor and the effective stress taken by the entire rebar group. So first we do it for the tension bars. Okay, so we cycle through all the tension bars. Okay. Now this, if you recall, this data structure was storing in the first two columns the x and y coordinates. Okay, so this is x and y coordinate of the particular bar. Okay, so we get x coordinate, y coordinate, and since in thermal we have only modeled one half, okay, what we say is that if this x coordinate is more than b by 2, okay, which means if you are talking about this bars, it is effectively same as the x coordinate of this bar from temperature calculation point of view. Okay, we are only looking for the temperature. So from here we get that. Okay, and now we know the coordinate x comma y where temperature is to be calculated, and this temperature will be temperature of the rebar. So we get this, calculate nx, ny, and we get the temperature of ith bar. Okay, so ns is the same as earlier for this particular time step. Now nx and ny are recalculated, okay, and we get, based on the fire temperature, we get Ts tension I. So this is like Ti that we were doing in case of nomenclature earlier. Okay, tension member temperature, or temperature of the ith tension rebar. Once we have calculated this, okay, then we calculate this rebar strength reduction factor using that the graph that we have discussed earlier. Okay, so that is calculated, and we also calculate the area of cross section of the rebar. Okay, so remember that in the rebar data structure, the third column was storing the diameter of the bar. Okay, using that, we are calculating the area, which is simply area of a circle. And this A tension I, which means this A. Okay, now here, since we have two layers, we have to worry about A fire. It will change with temperature because the lower layer will be at a different temperature, upper layer will be at a different temperature. So for each rebar, we can define AI. Okay, so this AI is the y coordinate. Okay, so this particular data structure, first column was x coordinate, y coordinate, third was diameter. So this second column we are using, which is y coordinate, that y coordinate will be the A. AI. Okay, so for each rebar we will calculate this. This is A for each rebar. Similar calculations we do for compression reinforcement. Okay, so now for each compression reinforcement, we find out the x, y coordinate. Okay, this is again the first and the second column. And similar to what we did for tension, if the x coordinate is here, which means more than b by 2, in that case, we go back to the corresponding bar on the left hand side, because here we are only worried about temperature calculations, which are same for both sides. So now we have these xy coordinates, so we can calculate temperature of the ith compression bar. Okay, so this again is Ti, but on the compression side. From the temperature, we can calculate strength reduction factor for each compression bar, and then we also calculate the area of each reinforcement bar as AI. Now that we have calculated the basic information and temperature calculations, we can go to strength calculations. Okay, so these strength calculations we are doing for each time that we are interested in of the ISO standard curve. So you may recall that for the average stress that can be taken by rebars, we had two possible approaches. One was we calculate average temperature of all the bars, and then from using that we calculate the average reduction factor, and then from there we calculate the rest of the things. But then there was a more accurate formula that we devised, which is a weighted average or a centroid calculation. Okay, so here we are using that. Okay, so this particular formula is coded here. We are saying FSD fire is summation of the reduction factors, which is this FSD for each bar, which will be same, and AST for each bar, which can be different, and this is divided by summation of all the areas. Okay, so this gives us the average, and from here we are calculating the FSD fire, which is this summation divided by this. Okay, so the first row, this is for tension side, the second row, this is for compression side. Okay, so for both tension reinforcements and compression reinforcement, we have calculated the strength reductions, reduced strength rather. Now for lever arm calculations, we require A. Now since here we have two layers, A fire will be different. Okay, and for A we wrote this formula. This is also a centroid type calculation formula. So we have A tension, this is AI, times K, which is this FSD, which is this, although it happens to be same for all the bars. A tension, which is this also happens to be same for all the bars in this particular case. Okay, so this is the numerator. In denominator we have K multiplied by F multiplied by A. Okay, so this is in a way A fire. Okay, this will be the distance of the effective centroid depth on the cross section. So now we can calculate this small d fire. This is the updated lever arm, which is capital D minus this A, which is A fire. Okay. Now this Z dash is the lever arm for the compression side reinforcement. This is for MU2. Okay. So Z dash is simply D fire minus this, which is this D dash. Okay. And notice that this D dash will not change because there is only a single layer of compression reinforcement. Then this lambda, since this is M40 grade, so lambda will be 0.8, but the formula coded in here is generic, so it can be used for any FCK. Okay. So then we calculate depth of the neutral axis. This depth of the neutral axis is summation of the AS tension times FSD fire. Okay, this is the tensile side forces divided by B fire times lambda times FCD. So when we are doing hand calculations, we had a greater look at how this formula works. So we get the depth of neutral axis, and then we calculate Z, which is the lever arm for the balanced section. Okay, so lever arm for balanced section is D fire minus lambda times x by 2. This also we have seen earlier. So with this we have all the necessary numbers to calculate the moment capacity. So we then calculate MU1. Okay, MU1 is the balanced moment, and then we calculate MU2. MU2 is the moment corresponding to compression steel and equal amount of tension steel. Okay. So the overall capacity as a function of time will be simply MU1 plus MU2. Okay, these two. Now we have divided them by this 1000 just to make sure that the overall units we get is in kilonewton meter. So we do this for the entire time duration of 4 hours, which is a 4-hour exposure to the standard fire curve. Okay. Then we can plot a graph between moment capacity and time. Okay. So the initial cold moment capacity is around here, 180, which is significantly higher than the demand, which is 120. But as time increases, okay, so as time increases, you recall that the temperature also increases. Okay, so ISO 834. Okay, this is an increasing temperature. There is no decay. Okay, that is where it is possible to do a one-to-one correlation of time with temperature, because this is an increasing function. Okay, so as time increases, temperature also increases, and the strength consistently decreases. and there is a time at which the strength or the capacity goes below the demand, right? So the demand is this. Demand is 120 kilonewton meter. Okay, and the time that at which this capacity goes below the demand, that is the fire rating of this beam, or the strength which is available after this is not sufficient to manage the demand. So in this case, we see that the fire rating is just a little bit over 1 hour. Now let us look at one more example, again done through a similar type of computer code. Although in this case we have considered a simpler scenario where there is a single layer of reinforcement. Okay, there is no two layers, so A fire will not be different from A. Now in this case, the carrying capacity required or demand is 70 kilonewton meter. Okay. FCK is M40, so again eta will be 1 and lambda will be 0.8. Diameter of the tension reinforcement is 16 mm, so 3 bars of 16 mm, and diameter of the compression reinforcement is 12 mm, so 2 bars of 12 mm. We start with the given data. B is 150 and capital D is 350. That is what we have. FCK is 40. Okay. FCD, you will recall that FCD is eta times FCK, and eta being 1 in this case, it will be same as the FCK. Okay. Then in both cases, for compression steel as well as for tension steel, the reinforcement is Fe415. And this is the demand moment. The data structures for compression and tension steel is same as earlier, where first column is the x coordinate, second column is the y coordinate, and third column is the bar diameter. Okay. So for this first bar, we have x coordinate as 30, y coordinate as 30, and 16 mm is the diameter. For the second, x coordinate is 80, which is 30 plus 50, y coordinate remains 30, and diameter is also same as earlier, 16. And for the third one, which goes in the third row, x coordinate is 130, y coordinate is 830, and diameter is again 16. And here also in the cross section diagram here, we have labeled this bar and this bar both as 1. And the reason for that is that for a 3-sided exposure, which is what we are considering here for the beam, there will be a line of symmetry. So the temperature of this bar and this bar will be exactly the same. For compression side, we have first this row, which is 30 is the x coordinate, 320 is the y coordinate. Okay, so y coordinate will be coming from here, and 12 is the bar diameter. Similarly, for the second row corresponds to the other rebar. 130 is the x coordinate, 320 is the y coordinate, and 12 is the bar diameter. Then we proceed with thermal analysis of the section. Again, we are modeling time up to 4 hours. Okay, and for the purpose of thermal analysis, we are modeling only half of the side because it is symmetric. Okay, we use a similar data concepts where x, y forms an ND grid. This gives the x and y coordinate like a grid on this beam. Tf is the fire temperature, which is again the ISO standard 834 graph. Some of you may notice that we start time at 0.1 and not at 0 because initially it's all at 20 degrees. So again, we calculate all the temperatures on the cross section at Txy, which can be used to plot a contour. So in this I have included these commands to plot a contour. So this xy is created by that ND grid function. Okay, so that goes as the first and the second argument. and the function we have calculated, in this case temperature, that goes here. Okay, and when we say here this end, which is we are trying to plot contour at the end of time, which is at 4 hours. Okay, so like this temperature contours can be plotted. So the figure that we saw earlier, it has been plotted using this kind of a approach. Now B fire will be B minus 2 times x500. Capital D fire is there, although we do not require at this point in time. Then we go on to calculate rebar temperatures. So similar to earlier, we go first towards tension reinforcements. Okay, first two columns are x and y coordinates that we calculate. If x coordinate is more than b by 2, which means if it is lying on this side, we take the x coordinate here because temperature of this bar and this bar is same. Temperature of this bar and this bar is same. Then using Wickstrom's approach, we again say nx, ny and this, alright. We calculate Ti, which is this temperature of each rebar. From there we go to the strength reduction factor, Ki for each rebar. This is area and this is small a. Right, so small a is this. And because we have a single layer, in this case small a is not going to change. When we do similar calculations for the compression side, okay, so you can look at it that we have xy coordinate just like earlier, and then again if it is on the right hand side we take it to the left hand side because we have used symmetry, and then we calculate Ti, Ki and area. Now from temperature calculations we can go to strength calculations. Okay, so FSD fire, it is a similar expression that we had earlier, that summation of this divided by summation of area. Okay, so we do that for tension side as well as for compression side. From there we go on to calculate A. In this case A will not change much, right? Then rest of it is same as earlier. So you will notice that the computer code remains the same. Okay, only initially we change the input parameters. So we have Z dash, which is lever arm for the compression steel and tension steel MU2, and then we have Z, which is lever arm for MU1. Okay, lambda will be 0.8 because the strength is 40 MPa of concrete. Then we calculate the neutral axis, and then we can calculate all that. So then we have MU1, MU2, which is for balance section MU1 and for the compression steel part MU2. So the total moment capacity will be MU1 plus MU2. Again we have divided by 1000 to make sure that units are now in kilonewton meter. So now for this, just like we did earlier, we can plot moment versus time. Okay, and since we are talking about an ISO 834 curve, increase in time implies increase in temperature. Okay. So moment capacity initially is here, then it drops. So now we can find out what is the fire rating. Okay, fire rating is when the moment capacity becomes below the demand. Okay, so in this case it is approximately 0.75 hours or maybe 45 minutes. Okay, so previous case fire rating was higher, beam design was also different. In this case it is 45 minutes. Okay, so this is how we can do detailed calculations to compute the strength or the capacity of beams. Now let us look at some provisions of IS 456. So the clause 21 of IS 456 provides some guidance on fire resistance. So what does it say? It says that a structure or structural element required to have a fire resistance should be designed to possess an appropriate degree of resistance to flame penetration. Okay, this is integrity, heat transmission, this is insulation, and failure. Failure is the calculation, the kind of calculations we had been doing. The fire resistance of a structural element is expressed in terms of time in hours, which is the fire rating, in accordance with IS 1641. So 1641 is a standard which gives some tabulated values and also gives definition of some of these things. Okay. But these definitions we have already covered in the lecture. So fire resistance of concrete elements depend on the details of member size, cover, steel reinforcement detailing, type of aggregate, okay, used in concrete. It also depends on loading conditions. Okay, we will have a brief discussion on that. Now, general requirements of fire protection are given in IS 1642. So 1641 is the first code to be referred. 1642 gives tables where we can have different sizes of beams or columns or slabs, and we can see how to get fire resistance rating based on those tables. Now, in addition to this 1641 or 1642, the IS 456-2000 itself also contains tables which give minimum concrete cover or minimum width of a section required to ensure a certain fire rating. So this says that minimum requirements of concrete cover and member dimensions for normal weight concrete, okay, so as to have the required fire resistance rating shall be in accordance with this and figure 1. We will look at figure 1 shortly. Now, when we look at figure 1, we will see that in certain cases the cover or the clear cover becomes very high. So what the code says is that additional measures such that application of fire resistance finishes, provision of fire resistance false ceilings, okay, and sacrificial steel in tensile zone should be adopted in case nominal cover required exceeds 40 mm for beams and 35 mm for columns. Because the code is aware that at higher temperatures, unconfined concrete, which is very weak in tension, can cause significant amount of spalling. So when covers are high, in that cases, instead of continuing to increase the cover to achieve a required fire rating, it is better to apply additional insulation material on top of the RCC beams or columns. And then one of the clauses says that specialist literature may be referred to for determining fire resistance of the structures which have not been covered in figure 1 or table 16a. So we will look at these tables 16a and figure 1. However, the code allows for use of specialist literature or calculations. Okay, so we have been learning these methods to determine fire resistance through calculations. Okay, and as per this code also, we can use all of these calculations to demonstrate or to assess whether our structural system has the necessary fire rating or not. So here this particular snippet is from figure 1. Okay, so this is figure 1 of IS 456 and this is table 16a. So figure 1 I have truncated here only for beams, although it gives values for slabs and walls also. We will see that in a different lecture. But what we have is one column is fire resistance rating in hours. So we have 0.5, 1, 1.5 like that. And the other column gives minimum beam width or B. Okay. So as per this table, for a half hour or 30-minute fire rating, we require a minimum width of the beam to be 200 mm. Okay. So this gives minimum dimension requirements for beams. And this is figure 1. Table 16 gives nominal cover to meet specified period of fire resistance. Okay. So as of now we focus on beams. We can look at the other parts later. So there are two support conditions considered. One is simply supported beams and one is continuous beams. Okay. So again, for half an hour fire resistance for a simply supported beam, we require 20 mm clear cover, nominal cover, clear cover. Same for both. So we will see that as we go on to have higher requirement of fire ratings, the cover requirement in simply supported beams is greater as compared to that of continuous beams. Okay, and it has also indicated that when cover goes beyond 40 mm, okay, then the beams become very prone to spalling, and in that case it is better to include some additional thermally insulating material to provide the necessary fire resistance, because eventually we have to prevent rise of temperature inside the beam. Okay. So let us look at how this works with respect to the two beams we have analyzed. The first beam the second beam we analyzed, the minimum dimension was 150. Okay, obviously it is below this. So what will be, we can conclude probably as per code, is that fire rating should be less than 30 minutes. Okay, clear cover is a little over 20, so this is 30, and we had 16 mm bars, so 22 mm clear cover. So from clear cover point of view, it can probably go up to 1.5 as per the code. However, from minimum dimension point of view, the rating should have been less than 30 minutes at least. But what we calculated was here, which is about 45 minutes, 0.75. Okay, so this is an example where one can say that, because 150 is not available here, it is better to use specialist literature, which is what we have used here. The other example that we did, the beam width was 230 and beam depth was 400. Okay, so in this case, we'll see that minimum here all the way up to 2 hours, minimum required is 200. Okay. Now it is difficult to conclude from here what will be the fire rating. Should it be 0.5, this, but I believe that is not how these codes have to be looked at. So this is minimum, but this minimum may not ensure this amount of fire rating. Okay, so from here one may be tempted to conclude that for a 2-hour fire rating we need a 200 millimeter beam. So any beam which is wider than 200 millimeter should have a fire rating more than 2 hours, whereas the fire rating we obtained was a little over 1 hour. Okay, same thing is true in terms of cover. Okay, so in this case, the clear cover would be 40 minus this 8, so it's a 32. So again you can say from the cover point of view that rating should be 1.5 hours or more. Okay. However, actual calculations show it is just a little over 1 hour. Okay. So this is where these codified tables may be seen as an initial guideline. However, it is really important to do these calculations to actually assess how much is the fire rating. When we were doing these 500-degree isotherm calculations, I said that we will discuss a little bit about how to locate the 500 isotherm. Okay, so this is a function that we have been using throughout the code. It takes as an input the TXY matrix that we had discussed, that it has, each matrix is at one time step. Okay, so it takes that and takes the section factors, section dimensions. Okay, then it goes through that matrix. Okay, and it finds out X500 and Y500. It will be useful to see what this X500 is. Okay, this is an output of the contour function. Okay, and this output is a 2 by n matrix, which is shown here. The first column, first row is the level. So if you are doing a 500 isotherm, this will be 500, and second column is the number, which is the number of such points. Okay, then each column gives the x and y coordinate of a point lying on the 500 isotherm. Okay, so each column gives the x and y coordinate of the 500 isotherm. So once we have that, then we are able to use that for locating the 500-degree isotherm. So in summary, what we have seen is that we have revisited the design philosophy for limit states. Okay. In the previous lecture, we saw in detail the material properties of concrete and reinforcing steel. We looked at the basic assumptions behind the 500 isotherm method, and we looked at how this method can be used to design flexural members, and we did a few examples. Okay, and finally we also looked at provisions of IS 456 for fire resistant design and how actual calculations match or not match with the codal stipulations, but we discussed a way of how these codal stipulations are to be used.